Welcome, Atreya, to my office. Your own office is actually not that far away because you are in the Physics Institute of STU, and it's in that direction, I can tell you. So it's not that far away. But welcome to my office. I'm very happy to see you here because I did a video about one of your papers not too long ago about the starburst galaxy M82.
That's correct.
Yeah, where you are using your membership of the Veritas network or Veritas Alliance. I don't know what you
collaboration.
Collaboration, Veritas collaboration, and Veritas is like reminds you of in vino veritas, the truth, but
Yes.
I think it's short for very energetic radiation imaging telescope array system or something
Perfect.
like that.
That is exactly what it is.
Yeah, so it's something that you're a part of a group that
Yes.
you are working together with for your research.
Mm-hmm.
But we're not here to talk about M82 because you also studied other objects.
Yes.
And I read your latest paper. It's about a blazar, and you're using a neutrino observatory. Can you tell me a little bit about that and also the viewers?
Of course, my pleasure. So, as the viewers would know, if you look around this, what you see is visible light. But that is only a very tiny fraction of all the light out there. So if you go to high energies in visible light, you have the ultraviolet. Above that, you have the X-rays, which our viewers will be familiar with, but hopefully not too familiar. And if you go to the really high energies, we have the gamma rays. So what I'm a gamma ray astronomer. So I look up and I try to find the most energetic light particles out there, the gamma rays. Now, up out in space, we have these things called black holes, and they accelerate particles to really high energies, like higher energies than we can here on Earth with CERN, for example. And this is sort of the idea behind it, is we want to understand how these particles are being accelerated out in space. And so these particles, they're called cosmic rays, and they're coming from all over the universe, and they're bombarding us. So if I put my hand out of the window, I get lots of cosmic rays bombarding me. Now, these cosmic rays are charged particles, right? Now, because they're charged particles, they get deflected by the magnetic field of the universe. So they do not travel in straight lines. It's a bit like me when I learn to drive. They don't travel in straight lines. So, in fact, what happens is we cannot see a cosmic ray and tell directly where it's coming from. But instead, what we do is we know that when a black hole emits cosmic rays, we know that it also emits gamma rays and neutrinos. So we use gamma rays and neutrinos, which are both uncharged and therefore do not interact, to basically answer the question, where are these cosmic rays coming from and what is producing them?
Yeah. So you're using this method,
yes.
You can say, to study very distant astronomical objects.
Yes.
And I think that the difference between the starburst galaxy M82 that you studied and the new one is that the new one is an active black hole.
Yes.
Really.
Yes.
So how far away is that?
So this one would be at a redshift of 0.15, which is quite fascinating because, as the viewers will know, when we're looking out in space, we're actually looking back in time. The light we see is actually from many, many thousands of years ago. So we're actually looking back at history.
Yeah.
But not just any history. We're looking back at our history. So light we saw from this black hole was from roughly 2,000 years ago, which to me is fascinating.
Yeah. Allow me a little bit of an excursion here because I recently did a video about Ole Rømer, the Danish astronomer and physicist, and many other things, who measured the speed of light back in 1676.
Yes.
And he didn't really know if light had a speed, if it was instantaneous. So an infinitely high speed, really. But I mean, if light didn't have a very high speed but was infinitely transmitted, you would actually not be able to look back in time.
Exactly.
So I think that's fascinating.
Isn't that amazing?
But modern astronomy owes to the fact that light does have a speed, very high one.
Yes.
So we can look back in time.
Yes.
So this blazar project, you used the Veritas collaboration, but also a neutrino experiment, and you said that you have all these particles emitted, gamma rays that you're looking at as a gamma ray astronomer, but also the neutrinos. And
Yes.
why are the neutrinos interesting in the context of this blazar?
This is very true. So neutrinos, basically, if a particle emits gamma rays and neutrinos, we believe that they come from the same processes from cosmic rays. So if something is like two clues which we put together and say if it's gamma rays and neutrinos, then it's very particularly the cosmic ray source. And we use the ice cube neutrino observatory in the South Pole to basically measure the neutrinos. And when it measures the neutrinos, it sends out alerts to telescopes such as Veritas, which, as the viewers might know, is in Arizona. We also have HESS in Namibia and MAGIC in La Palma. And basically, it sends out alert to these ground-based telescopes to follow up. And basically, that's what we did. They sent us an alert, we followed it up, and we basically did. So that when the neutrinos are being emitted, is it also emitting gamma rays in high state? And basically, we compare the neutrino emission to the gamma ray emission.
Yeah. So the idea is, as you said originally, that these kind of cosmic rays don't travel in straight lines.
Yes.
Because they're deflected, for instance, by interstellar or intergalactic magnetic fields.
Yes.
But the neutrinos that interact weakly with normal stuff can go more directly and straight, and
Yes.
therefore you can observe them perhaps even before the radiation that is normal.
Yes.
So one place where or one context where this is also relevant is with supernovas. So I've talked about that earlier in some videos, particularly because I'm interested in the red supergiant star Betelgeuse that might go supernova, where some Japanese scientists have constructed a kind of a neutrino alert system to observe the neutrinos before the supernova goes off, because they the neutrinos are presumably, according to models, will be transmitted earlier than the normal light. So this is the same here, but you're looking at extra-galactic objects.
Exactly, stuff from far, far away.
Yeah. So this observatory is at the Amundsen station, I think, in the Antarctic.
Yes.
So it's a really cold place. I guess that's why they call it the Ice Cube Observatory.
This is true. It's literally under the ice. It is a cube under the ice.
Yeah, very far, deep actually buried. Very interesting. A lot of detectors to detect the Cherenkov radiation.
Yes.
From when the neutrinos react in the detectors on the ground.
And for the viewers, Cherenkov radiation is when something moves faster than the speed of light in ice or in water. You know, nothing, as we said earlier, moves faster than the speed of light in vacuum, of course.
Yeah. So these observations where you compare the gamma rays from the blazar to the detections of neutrinos from the Ice Cube Observatory, what do you find?
So you mean in these specific observations?
Yes.
Okay, so usually what we did is this whole thing started from a 2017 paper when they found a blazar TXS0506. And they found that when the blazar emitted neutrinos, it is also in a very high state where it is very bright in gamma rays. So they found a correlation between the neutrinos and the gamma rays. Now, for us in our paper, well, fortunately or unfortunately, it is science, of course, but we did not find any correlation between the neutrino and the gamma rays, because the neutrino was emitted when the source itself was in a low, what we call a quiescent flux state.
All right, so what you do actually have is a non-detection.
Yes.
And I think that's very, very important, because science is not always about proving that something is correct. It's also about falsifying. It's also about having results that don't show what you thought, because that's where you learn.
Exactly. It's about having an open mind, right? And seeing where we end up. The data is the data. And here, what we found is that it's a non-result, but we still derived upper limits, and that is also the viewers contributing to the science.
Indeed. So that's actually very important. What will be your next, or maybe what are you working on now? What will be the next paper?
So I've actually moved from Veritas to HESS, which is another collaboration in Namibia. And right now what we're doing is we're looking at, as viewers will know, there's this thing out there called dark matter, which we don't really know, which also makes it very exciting. And there is this dark matter candidate called axions. And I'm looking at data from blazars again to see if we find any signatures of these axion-like particles in the data.
Oh,
So that's my new project, which I'm currently working on.
exotic particles.
Yes.
Yeah.
Yes.
And actually, at SDU, we have some colleagues also working with that context of,
Yes.
of exotic particles. Regarding the Hess
Yeah.
network, I think I actually did a paper on that earlier on. So I'll, or not a paper, but a paper video on that
Yes.
earlier on. So I think I will put the link in the
Brilliant.
description of the video here.
Sure.
But I also look forward to do a video on your next paper then.
That'll be amazing. Let's schedule a date in 6 months then.
Let's do that.
Yeah.
Thank you very much for coming.
My absolute pleasure. Thank you for having me.
I hope you enjoyed this video with Atreya. So see you back sometime.
See ya.
Bye.
Bye. Be safe.